Welcome to the deep dive. Today we're looking at something, well, potentially huge, severe solar storms, especially as the sun ramps up towards its peak activity around 2025.
That's right. This isn't just academic interest. These events could really impact our daily lives in pretty profound ways.
Because we're so reliant on technology now.
Exactly. The sun has this cycle, roughly 11 years, and heading into the maximum, the chances of really big flares and eruptions, they just go up.
And we're not just talking about pretty auroras, are we? I mean, historically.
Well, the auroras are part of it, definitely. But yeah, history gives us some stark warnings, like evidence in tree rings points to this monster radiation burst maybe 13,000 years ago.
Wow, 13,000.
Yeah. And more recently, well, relatively speaking, you have the 1859 Carrington event.
Ah, yes, the famous one. That hit the telegraph system hard, didn't it?
It completely fried telegraph networks globally.
Yeah.
Imagine 19th century tech, and the sun just knocked it sideways.
Which really makes you think, if it did that then, what could a similar storm do to our world now? Our grid, satellites, everything.
That's the million-dollar question, isn't it?
Yeah.
Or maybe $1 trillion. How ready are we, really? It's something scientists, grid operators, policymakers, they're all grappling with.
Okay, so that's our mission for this deep dive then. We'll look at the threats these geomagnetic storms pose, what we're doing about monitoring and warnings, the good and the maybe not so good parts.
And how we're trying to make infrastructure tougher, hardening the grid, protecting satellites.
And crucially, how everyone coordinates when, the big one hits.
Okay, let's start with the basics. What actually happens? How does the sun cause these storms on Earth?
So it starts with the sun spitting out these enormous clouds of charged particles, plasma, basically. We call them coronal mass ejections, or CMEs.
Right, CMEs, I've heard that term.
And when one of these clouds slams into Earth's magnetic field, our magnetosphere, that's when the fireworks start, literally and figuratively.
Figuratively meaning the problems, literally meaning the aurora. You got it. The interaction energizes particles in our atmosphere, creating those amazing northern and southern lights. Beautiful stuff.
But the dangerous part.
The dangerous part is that this massive electrical interaction up high can induce powerful currents in the ground. Geomagnetically induced currents, or GICs.
Okay, ground currents. Why are they the bad guys here?
Because our power grids are, well, grounded. They use the earth. So these extra powerful currents can flow into the grid where they shouldn't be.
And they can overload things.
Exactly. They can surge into high voltage transformers, cause them to overheat, melt windings, basically permanent damage, leading to blackouts.
Not just flicker the lights, blackouts, but potentially long-term ones.
Potentially very long-term, yeah. If you damage enough critical transformers, replacing them takes months, maybe longer. We're talking widespread disruption.
Okay, that's the power grid. What else is vulnerable? Communications.
Definitely. Radio communication can be disrupted. Even undersea cables, which carry a huge chunk of global internet traffic, they can be affected by these induced currents too.
Wow. And satellites? They're kind of exposed up there.
Very exposed. The charged particles can damage their electronics, degrade solar panels, even cause total failure. Think about weather satellites, communication satellites.
Yes.
GPS is a huge one. Losing accuracy or losing the signal altogether, that impacts planes, ships, trains, farming equipment, financial networks.
Autonomous vehicles, too, increasingly.
Absolutely. The reliance is just growing and growing. So a major GPS outage. That's not just inconvenient, it's potentially dangerous. Grounding planes, stopping ships.
And this isn't just theory. We've seen smaller examples, right? You mentioned the Quebec event.
We have. March 1989. A storm, less intense than Carrington, knocked out power to millions in Quebec for about 9 hours.
9 hours is still a long time for that many people.
It is. And it also caused damage at a power plant down in New Jersey. It showed the interconnectedness and the vulnerability.
And even more recently, didn't we have something just this May? The Mother's Day storm?
We did. That was a great example, actually. Stunning auroras seen way further south than usual. But it also caused some reported disruptions to things like farming GPS and interference with some radio signals.
So a bit of a wake-up call, even though it wasn't catastrophic.
Exactly. A reminder that the sun is active and our systems are susceptible. It keeps the issue front and center.
Okay, so Given this real and present danger, how are we doing on the monitoring and early warning front? Are we getting better at seeing these coming?
We've definitely made progress. We have satellites constantly watching the sun, like the SOHO and SDO spacecraft, and ground-based telescopes, too. They give us eyes on solar flares, CMEs lifting off.
So we can see them leave the sun.
We can. That gives us some warning, usually 1 to 3 days for a CME to travel to Earth, depending on its speed.
But I sense a but coming. What are the gaps? The challenges?
Well, the big one is forecast accuracy. We can see a CME is Earth-directed, generally, but predicting exactly when it will arrive, and crucially, how strong the impact will be, especially the orientation of its magnetic field, which is key for GICs that's still really hard.
Kind of like forecasting a hurricane's exact landfall intensity.
That's a pretty good analogy, yeah.
Yeah.
We know it's out there, we know it's coming, but the precise details that determine the impact are tough to nail down perfectly in advance.
Okay, prediction accuracy. What about just seeing them? Do we have enough eyes in the right places?
That's another area for improvement. Most of our key space weather satellites sit at Lagrange point 1, L1. That's between Earth and the Sun.
Gives us a direct view.
It does. But it doesn't give us a good side view. Ideally, we'd want more assets, particularly at Lagrange point 5, L5.
L5, where's that?
It sort of trails Earth in its orbit, off to the side. A satellite there could see the parts of the sun rotating towards Earth before they face us directly.
Ah, so it could spot eruptions happening on the sun's side, giving us earlier warning.
Exactly. Potentially an extra 24, maybe 48 hours warning for some events. That extra time could be absolutely critical for preparing the grid or putting satellites in safe mode.
That sounds incredibly valuable. Is getting something to L5 a priority?
It's definitely discussed. Agencies like ESA have plans, but it requires significant investment in international cooperation. Which brings us to another point, data sharing.
Right. You can have the best satellites, but if the data doesn't get where it needs to go, fast.
Precisely. We need smooth, real-time coordination between NOAA, NASA, ESA, military space weather centers, everyone involved globally, getting the right data interpreted correctly into actionable alerts for grid operators or satellite controllers. That process needs to be seamless.
Streamlined protocols, maybe common standards.
All of that.
Yep.
Otherwise, like you said earlier, everyone's just playing catch-up when the storm hits. We need robust international collaboration, sustained funding, and better data pipelines.
So improve the forecasts, get more eyes at places like L5, and make sure everyone talks to each other effectively.
That's the gist of it on the monitoring side, yeah.
Okay, so let's say we get a better warning. What about the infrastructure itself? Can we make it tougher? What are grid operators and satellite folks doing?
They're definitely taking steps, learning from past events and research. For power grids, they're installing more sensors specifically to monitor those geomagnetically induced currents, the GICs.
So they can see the threat building in real time.
Exactly. And they're developing procedures to quickly reconfigure the grid, basically, change power flows, or temporarily isolate vulnerable parts to limit damage if a storm hits.
Like redirecting traffic around an accident?
Kind of, yeah. And they're also deploying hardware fixes, like series capacitors, which can act like blockers for these harmful DC-like currents from GICs while letting the normal AC power flow.
Interesting. Okay, so sensors, procedures, hardware. What about up in space? How do you shield a satellite?
It's tricky, but engineers are designing electronics to be more radiation hardened, basically tougher against particle bombardment. Redundancy is key too, having backup systems ready to take over if a primary component gets zapped.
Makes sense, like having a spare tire.
Exactly. And also developing safe modes. If a big storm is coming, controllers can shut down non-essential or particularly sensitive instruments and orient the spacecraft to minimize exposure, riding out the storm in a protected state.
And what about communication links if satellites are having a bad day?
Good point. Having backups is vital. Relying solely on satellites for critical comms is risky. So ensuring robust terrestrial backups, enhanced radio systems, fiber optic networks, that's part of the resilience picture too.
Now all this hardening, sensors, capacitors, rad-hard electronics, backups, it sounds expensive.
It absolutely is. There's a significant cost to implementing all these measures.
And utilities, satellite companies, governments, they have to weigh that cost against the risk of a catastrophic event, right? Which might happen tomorrow, or not for decades.
That's the crux of the economic and policy challenge. How much do you invest in preparedness for a low-probability, high-impact event? The very difficult calculation, balancing resilience investment against the potential, well, civilization-disrupting costs of not being prepared.
High stakes indeed. Okay, so we have the threat, the monitoring efforts, the hardening strategies. How does this all come together in terms of response? Who coordinates?
Coordination is absolutely critical, and it has to happen across multiple levels: government agencies, private industry, international partners.
How do you practice that?
Tabletop exercises are one key way. Actually, Johns Hopkins Applied Physics Lab, APL, just ran one this past May.
Oh, perfect timing. What did that involve? Who was there?
It was really comprehensive. It brought together space physicists, weather forecasters, people who actually operate satellites and power grids, emergency managers, folks from tribal agencies, NASA, NOAA, a real cross-section.
So all the key players in one room, metaphorically speaking.
Pretty much. And they threw scenarios at them. Things like, okay, a major storm is incoming. How do you get warnings out effectively? Or the grid has gone down. How do you coordinate a black start to bring it back online safely?
A stress test for the system, basically. What came out of it? Any big takeaways?
According to Ian Cohen, who led the exercise science there, it really highlighted gaps both in the science, like those prediction challenges we talked about, and in observational capabilities.
Okay, confirm some of the things we've discussed.
Right, but just as importantly, he said it was crucial for getting scientists comfortable communicating complex risks clearly and actionably to the people who have to make the operational decisions, bridging that gap between research and response.
That communication piece is always so vital in a crisis, isn't it? Translating the science into what do we do now?
Exactly. And the exercise resulted in an after-action report with some pretty clear priorities.
Okay, what were the big ones?
A major recommendation was for a unified notification framework. Basically, one trusted authoritative source for alerts, but tailored for different users.
So the power company gets the specific GIC forecast they need, the airline gets the radiation or GPS impact warning, all from one system.
That's the idea. Avoid confusion, ensure consistency. Another big one was strengthening interagency coordination, making sure NASA, NOAA, Homeland Security, state emergency agencies have clear protocols for sharing data, resources, plans.
Makes sense, breaking down silos.
Definitely. And public education was another key theme, making sure citizens, businesses, first responders actually understand the risk, know what simple preparedness steps they can take, and understand emergency procedures if something happens.
Empowering people beyond just the big infrastructure operator.
And finally, underpinning all of it, the need for continued research and development. Better forecasting models, better sensors, better hardening technologies. The work isn't done.
So unified alerts, better agency teamwork, public awareness, and keep pushing the science and tech seems logical.
It does. But the elephant in the room, as the APL report implies, is resources. Will governments and industry actually fund and implement these things seriously?
Yeah, the commitment question. Because as we head into this 2025 solar maximum period, the odds of a major event, statistically speaking, are higher.
They're undeniably elevated. It's a matter of probabilities, but the hazard is real.
Which leads us to some closing thoughts, some questions maybe for you, our listeners, to ponder, drawn from the material we looked at. Like, have our national emergency plans truly accounted for space weather? Is it treated with the same seriousness as, say, a hurricane or an earthquake?
That's a really critical point. And related to that, what are the real backup plans? If satellites go down, if the power is out for an extended period, how do hospitals keep running? Airports, financial systems, what keeps the essentials going?
And thinking bigger, globally, a major storm won't respect borders. How prepared are we for international collaboration during a crisis? Sharing power, coordinating communications, managing cross-border infrastructure impacts?
These aren't easy questions. They involve complex planning, investment, and cooperation. But they're essential to ask.
Because that star, 93 million miles away, fundamentally shapes our environment, and now it directly impacts the technology that underpins, well, pretty much everything in modern society.
Absolutely. Understanding that connection and preparing for its more extreme moments isn't just about protecting technology, it's about safeguarding our communities and our way of life. Being prepared is key.